Welcome everyone to C83 PFP. So you probably, hopefully, know why you're here if you've read the module description. We're going to be pretty gentle at first with your introduction to programming here, and then move into some more advanced topics later in the semester. So I will be sprinkling these comics from XKCD in periodically. Most of them you'll probably not understand at first because you are not big enough nerds yet in the Python world, but hopefully as time goes on they will become funnier to you. Okay, so let's talk about a few things about what we're doing in this module before we get too far along, what our goals are, what we're going to try to teach you guys to do. So as you probably read in the module description, our hope is that this will be a challenging but accessible introduction to computer programming. You don't have to know anything about programming already, which is good because I suspect most of you have not had a programming course before. And we're focusing on practical applications. So if we were starting on theory and stuff, it would take like 2 years to teach you about like data structures and algorithms and all this stuff. But I know you guys most of you don't really care about that kind of thing all that much. So we're going to try to, if you do, we can talk later. But we're going to focus mostly on practical applications. So for your purposes, we're going to focus on like how programming is useful to you as a psychology researcher or potentially as a person in psychology doing other things, but mostly on how these skills relate to your research career, at least for the rest of your time here at Nottingham. So that means how you're going to be able to use programming to design cognitive tasks for experiments, how you're going to be able to use it to analyze your data, and things like that. So cognitive tasks and stats and data analysis are the two main things. And of course, for that, in this way, we're going to focus on psychology and cognitive neuroscience, but these concepts would be useful everywhere. So if, at the end of this year, those of you who are final year undergrads decide that you never want to see another psychology experiment again, I hope you will still find these concepts useful in other places. So I'm hoping to do this class a bit differently than a lot of programming classes, because I think traditionally if you start doing like computer science or something like that, things start going pretty slowly. It's very dry at first, and I will warn you that today is a little bit dry, but hopefully even by like next class meeting, we'll be getting into doing like some simple tasks in PsychoPy. You'll get to see pretty quickly how this is potentially useful to you in your actual everyday life. So that's the hope, and we'll sort of gauge it and see how fast we can go through this class. But what I typically find, like in textbooks and things like that, is that the books go very fast and they don't start out being very interesting. So I'm hoping we can go a bit slower because people don't have a lot of experience with this, but also like get into the interesting stuff a bit sooner. So we'll see how that works. Okay, so as far as what we're going to do in the modules, so every class meeting will consist of about a 1-hour lecture. We'll take a little break, and then we'll do about an hour-long workshop. And by workshop, what I mean is it'll be a combination of me and you, sort of like, I'll still be sort of leading you through the workshop, but hopefully what we'll be doing is I'll say, all right, here's some code, type this in, see what it does. Now try to solve this problem, and then I'll give you a couple minutes to do that, and then check in with you and that kind of thing. So it'll be a little more interactive, but we'll start off with a lecture just to kind of introduce some topics, and then in the workshops we will try to explore those and give you some hands-on experience with them. And today is probably going to be a little bit more lecture heavy because you won't know as much to be workshopping. And the workshop is not going to be as coding heavy as it will be in the next few weeks. So the workshop is going to be a little bit more thinking oriented than programming, although hopefully we will get to type in some code by the end of the day. Okay, so the way that it's going to work out is we're going to kind of have a focus for each semester. So this semester, we're going to focus mainly on the Python programming language and this little guy, who some of you may already be familiar with, known as PsychoPy. And sort of practically speaking, the way it works out is because we won't actually have MATLAB installed on these computers until next year. So, so in January, we'll start to do MATLAB along with the Psych Toolbox. But partly, I think this is a good way to go anyway. So what we'll be doing is starting off teaching you guys the programming language called Python. And if you don't know already, PsychoPy is a piece of stimulus presentation software for use in psychology that is written in the Python programming language. And we'll talk a little bit more about that distinction later. But basically, the thing to keep in mind right now is Python is a programming language, and this is sort of a collection of tools that use Python. And with MATLAB and scikit-toolbox, it's kind of the exact same thing. MATLAB is this piece of software for computational analysis and data processing and things like that. It has its own programming language, which we'll be learning some of next semester. And scikit-toolbox is a collection of MATLAB scripts and programs that are focused on being able to deliver cognitive tasks. So that's the basic layout. So for the moment, you can just sort of forget about MATLAB. We'll be sort of foreshadowing some of the things we'll talk about for MATLAB, but we won't really be talking about it at all until next semester. However, just for your reference, a few basic things to keep in mind when you're thinking about which of these you might use in your future endeavors. So basically, the reason that we're teaching both of them is because both of these are super common if you stay in academia, or those of you who are PhDs or becoming PhDs who are already locked into academia for a certain amount of time. You will see these all over the place. So MATLAB especially is super common in cognitive neuroscience. Like if you ever do EEG or functional MRI, you're not really going to be able to escape MATLAB entirely. And Python is also very common. So basically, they're different things. So MATLAB is really a software package with a programming language built in. But MATLAB is very oriented about data processing and scientific applications. Python is a general purpose programming language, meaning you can use it to program a computer to do anything, but one thing that it's particularly good at is scientific and academic sort of applications. And one reason academics like Python is because it's free, both as in cost and as in like freedom of speech. So you can get the Python language for free, it doesn't cost you anything, you can install it in Scikit-Py right away. MATLAB is more useful for some things, but it's also really expensive. So if you're at a university that can hopefully buy it for you, that's usually not a big problem, but you wouldn't just go out and like buy MATLAB yourself because it's very expensive. So so that's one reason that people sort of choose different things. People that are all into like Linux and the free software philosophy and open source everything, they love Python a lot because of that. If you are more into like Macs and iPhones and things that actually work without too much tweaking, MATLAB may be your product of choice. So you can sort of, you might be able to guess that I come from more of a MATLAB type background, but I am gradually getting pushed over into the Python territory by my Python-loving academic friends. Okay, so we'll talk a little bit more about actual, it's okay, come on in. We'll talk a little bit more about actual Python and programming stuff in just a minute, but first let's just quickly outline what we're doing in each semester. So you see, semester one, we're not going to talk about this in depth, but basically these are the topics. We'll start out today just talking about some general ideas, but starting next week, oh actually I take that back, starting maybe 2 weeks from now, we'll really be starting to get into Scikit-Py. Next week we're going to be doing a little bit of basic Python programming and then get more and more into doing real type tasks with Scikit-Py as the semester goes on. And this is a very loose outline. This is going to be totally dependent on like how you guys are doing, how difficult you find this stuff. So we can slow down, we can speed up as you see fit. So we'll see how it goes, but this is a basic outline for how things will go. And then next semester, basically, what we'll be trying to do is cover all the same topics we covered this semester, but with MATLAB instead of Python, but hopefully a little bit faster because the basic concepts will already be down. And then towards the end, we'll do some kind of advanced topics and have some catch-up days and things like that, and have some days for you to work on your final projects. Okay, so just a little note on coursework. You may have already seen this in the class description, but a big chunk, this is a little bit different from most of your other modules. A big chunk of this class is going to be problem sets. You guys may have never had a problem set focused class, at least in university before, but if you do like a computer science major or a mathematics major, something like that, at least in the United States, and I assume here as well, you will do a lot of problem sets. So this is basically like a sheet of homework. I plan to do 10 of them, so about one every 2 weeks. So we'll actually do like we'll probably do, my math doesn't work out here. 10 Okay, I screwed up the math. Anyway, we'll probably try to do one more of them in this semester than next semester. Um, right, well, oh, yeah, that's what it is. About 10 each semester. Oh, I'm going to have to recompute some numbers here because I think I doubled something. Okay, anyway, we'll do them about every 2 weeks. Each one is actually going to be, should be 2% of your grade, because I keep forgetting we have 2 semesters here. So we'll probably do a few more in semester 1 than in semester 2. But anyway, basically you'll have one about every 2 weeks. If you do all of them perfectly, you've got a 40 in the class, which means you would actually pass already, although probably won't be totally perfect. But hopefully you'll be able to get a large portion of your grade from the problem sets. Then 30% of the class is your final project, not your final year project for psychology, but a final project for this module. 10% of which will just be doing a proposal for it, due in semester 1. 20% will be the project itself, due at the end of the second semester. And then 30% will be the final exam. I know this sounds like a lot of work, but the idea is that each one of these things is not going to be a super huge deal by itself, so that hopefully your overall grade will be distributed over all of these small projects and a relatively small final exam rather than having like everything in one big project. Because the idea with this course is that you're going to have to do like a little bit of work every week or every 2 weeks to sort of like help these ideas sink in and things like that. It's not going to be the kind of thing where you can just cram right before the exam and get a good grade, because you want to be developing skills kind of throughout the year. And so the problem sets and the projects are intended to help you kind of enforce that by like having you continually working towards a goal. Okay, and I need to tweak a few things in the first problem set, but I will be posting that to Moodle later today. So if you're able to get on this class in Moodle, that should be fine. And the postgrads and staff, I'll figure something out so that we can all get to that. Okay. So about coursework, just a note. If you're familiar with this meme, you probably also, like me, spend too much time on the internet. If you're not, this is an internet thing. But basically, I do want to just kind of let you guys know it is really important to come to lectures and keep up with problem sets in this class. This is not supposed to be like a really hard class, but it's cumulative. Okay, so it's it's not just information that you have to memorize, and if you skip all the classes, you can just kind of read all the lecture notes at the end and be okay. It's really more like a sport or a foreign language or lifting weights or something like that. So if you're lifting weights and you lift a slightly heavier weight every day, you'll be fine. By the end of the class, you'll be lifting heavy weights and you won't even notice. It'll feel effortless. But of course, if you try to start with a light weight on the first day and then don't show up all semester and then show up on the last day and try to lift the 100 kilograms, you're going to have a hernia and fall over. So, the idea is to hopefully do things gradually and make it pretty easy on you. So just keep that in mind. Hopefully everyone will show up. And if you practice it, this will not be too difficult. But it's the kind of thing you really have to develop a skill. You can't just hope to understand it the first time we go over something and then never actually use it till the exam. Okay, and by the way, that is also true for the postgrads and staff. So, I mean, if you miss a week here and there, I'm sure you'll be able to catch up with the podcast and so forth. But in general, it's good to sort of work on this stuff continuously. Okay. Couple other things. So just some notes on collaboration and such. So you will have these problem sets. And of course, collaboration is a really important part of both academics and programming. So usually if you're a professional programmer, of course, you work in a team with a bunch of other people, and some of you handle some things and some of you handle other things. So I do this, I don't know how it tends to work in other classes, but at least for this class, regarding the problem sets, you're going to be in here, you're going to be working on things. I think it's totally fine if you help each other out and explain concepts to each other and things like that. However, you just want to reinforce, because this is always a thing that we want to reinforce at the university, don't actually plagiarize anyone's answers or code. Everything you turn in should be all your own writing and all that stuff, right? So just wanted to sort of mention that. And in terms of projects, if people want to have multiple people work on a final project together, that's okay. But basically, I would want it to be that you can propose something where like everyone's sort of contributing a module or a piece of work to the project that we can assess individually, so that everyone doesn't have to, hang together or die alone or whatever that phrase is. So anyway, so that's some stuff to talk about. We'll talk more about projects in a week or two. So you don't have to worry about that too much now, and you don't really probably know, technically speaking, the kinds of things that you need to know about like how one person can write a code module that works together with someone else's, but we'll get into that. So that's just the general policy. There's a little bit more on the collaboration rules in the first problem set, but that's just to let you know. And again, for the postgrads and lecturers and so forth, you obviously don't have to use a project, but if you intend to do this stuff, to stick around for the semester, I think it would be helpful to sort of like pick a project that you're interested in or a little task you'd like to get working or something like that, so that you can have something to work on in your spare time that gives you like a larger goal to work towards. Because I know I only sort of recently started learning Python myself, and it always helps to have like a project, because you can like read through a book and be like, oh yeah, this all makes sense. I'm sure I can do this. But until you have an actual like project to work on, you don't always realize like all the little details that you're going to have to figure out. So I think it's good to have a little project to work on, even if you don't actually get a grade for this course. Okay. One last sort of little organizational note, or a couple of little last organizational notes on resources. As you may have seen in the course description, there's no required reading for this class, which hopefully is a good thing. Everything you need to know is going to be covered in the lectures and the problem sets. So the problem sets will help you kind of go over what we did in lecture in addition to the workshops, and also to maybe extend your skills a little bit to sort of push you just a little bit beyond the lectures. But you won't have to read like chapters and chapters of stuff. You don't have to download papers. You don't have to do any of that stuff. However, we would hope, so one goal of this module is that I'm not going to be able to teach you everything about all of this stuff, but what we hope is that you can get self-sufficient enough from what you learn in this module that you can do what real programmers do in real life, which is run into a problem and Google it and find some other programmer that had the same problem and figure out the solution based on something they find on the internet. So that said, I'm hoping that you'll be able to use resources that you can find online. Some good recommendations are the built-in help. So both MATLAB and both MATLAB and Python, but especially MATLAB, have really good built-in documentation. We'll talk more about that when we really get into each of those. www.python.org is the official Python website, which again won't be super useful to you until you have some basic concepts down. But once you do, like everything about the Python language is documented online, so it's all there. Once you become like a real nerd with this stuff, stackoverflow.com is a good website. So it's sort of like Yahoo Answers, but hopefully more intelligent. So like you can post a question on there, and someone will tell you like, oh, this is how you do this, and you can find a lot of good answers there. And there's a million other resources as well. The only sort of quote-unquote text that I'm recommending at all is a book called Learn Python the Hard Way, which is not actually the hard way. That's sort of the joke of the book title. So if you're interested, this is a book that is actually free online. You just Google it, and it's like learnpythonthehardway.com or .org or something like that. If you just want to view it on the web, the HTML version is totally free. If you have an e-reader of some sort and want the EPUB format, which will work on an iPad or I think a Kindle, I can actually send you that because I've already bought that, and they say it's like free for educational purposes if I give it on to you guys. And it's like $3 US if you want to buy a PDF version. So it's super cheap, but the HTML version is probably all you would ever need. But all of this stuff is totally optional. This is just for like when you get stuck on something and want to figure it out for yourself. So programming books are almost always pretty much awful, and like only good if you already sort of know the things in them. So I think mostly we're going to try to do it like with peer support and with me helping you out and that kind of thing. Okay. By the way, there are also a million books on Python and MATLAB in the library here. You may find some of them useful. I flipped through them when I was designing this module, and I didn't find any of them all that helpful, but your mileage may vary, so you're welcome to try them out. But generally speaking, what I would recommend for anyone starting out is like Google's your friend. Every issue you will come upon has been come upon by someone else already who has asked someone on an email list about it. And if you just sort of Google things, you will find answers. And of course, that's true because the entire internet is built by nerds who do this stuff all the time, right? So like, it's just full of this kind of information. They love to put this stuff online. Okay. One last note. You've probably already seen that we're doing this, but we are podcasting this. Basically, you might have noticed I didn't give you any printed lecture notes. And we are going fairly quickly in the lectures and the workshops. But I think a helpful way to do this, because you're not going to be able to get that much from just printed lecture notes, although I will give you the slides online as a PDF. But I think if you need to go back and sort of hear something again, see something explained again, this might work as a good way of finding this out. And one thing we might also do is make these available outside the university if it goes well. If it crashes and burns, nobody else ever has to see it, but we'll see how that goes. But that'll be the idea. So what I'm going to do is it'll be the slides and my voice explaining these things, and a little tiny box of my head, probably down on the side, maybe, if that works out. But I think that will help because, you know, you'll get to see things in action because, especially for the workshops in this class, we're going to be typing code in live and running it and doing it in real time. So slides don't really help you that much. You need to see how things are done. So we're going to try this out. This is also like a project for my PGCHE, so there's an ulterior motive in it for me also. But I think this will work out well as a way for like reviewing material and that kind of thing. Okay, so just be aware of that. Feel free to ask questions and everything as you would normally. Like I can always edit this or just, you know, chuck it completely if this goes horribly awry. But, you know, just sort of be aware of it. So try not to make too much extra noise and things like that. But yeah, totally feel free to like interrupt, ask questions, break in, that kind of thing. And there will be some audience participation. So like, you know, you're going to get on camera at some point, or at least your voice on. So just be aware that we're doing it. But yeah, try to keep down the background noise and everything. Okay, so any questions about anything before we start the actual class stuff? Everybody good? Everybody on track so far? Anybody confused yet? Okay. We're going to go, trust me, we'll be very gentle these first couple of weeks and then ramp it up a little bit as time goes on. Okay, so I am going to talk at you for a few minutes. Like I said, we're going to do lecture first and then jump into workshopping as time goes on. So first I want to talk to you guys a little bit about why you want to do this stuff. So why would you ever even want to learn to program? And we've sort of alluded to this before, but I do want to sort of push this point home that if you get into this and if you do well with this, I think this is one of the most generally useful things you can ever learn to do, aside from like driving and cooking so you don't starve and things like that. This is right up there with those things. And you know, if you keep track of these things, people say that in the future, this is going to be like a basic class that children learn when they're like 8 years old, along with their reading and their writing and arithmetic and all those things. I mean, they're already starting to teach little kids to code in like sort of basic little kid languages in some places. And you know, it's just going to be more and more the case as time goes on. And you may have seen online some of these projects like Code Academy. There's a project called Code Year where like you try to learn to code in some programming language over the course of a year. There are tons of classes on iTunes University and things like that on how to program. Like there's a great one on how to program iPhone applications and things like that. So you can learn all this stuff online. As you might guess, there is big money to be made if you know how to program. If the whole psychology thing doesn't work out and you want to be a computer programmer, you can always freelance or go write you know, dumb little games for Android phones and you know, make a lot of money, 99 cents at a time. You can save yourself a ton of time. So this is something that happens all the time. Like I'll tell you, for example, a colleague of mine back at Yale, so someone in my old lab, we would run studies with word stimuli, right? So psychology studies with word stimuli. And when you use words, if you're going to run a good study, like say you have two different conditions in your task, you want to have lists of words that are balanced with each other. Like they, you know, on average have the same length and same like difficulty and same frequency in the language and all this stuff, because you don't want your stimuli to have like confounding things different between them, right? And so what you have to do is you have to make sort of Excel files of all these things, like say, all right, what if I use these 30 words versus these 30 words? And what's the average frequency in each of these lists? And you t-test them on all these factors. And it would take her like weeks to do these things. And I had to do a study with words, and I was like, oh, we can just write a little MATLAB script to do this. And I was like, and then like an afternoon, we had like 100 word lists. So that's the kind of thing, like, it'll take you some time to learn this stuff, but then once you know it, you will begin saving yourself time. So it's really, really helpful for that kind of thing, for coding up tasks, things that could take you like weeks to kind of get just right in Excel or ePrime or whatever you can do in like an afternoon. Of course, there are like various other side benefits, specifically uses in psychology and cognitive neuroscience. But I think the biggest thing of all is that it will help you, and this is maybe a little bit too like lofty of a thought, but I really think it does help you organize your thoughts better, to think things through better, to think about like the logic of all of your actions better. So, the more you learn to program, you have to think about things like, if I do this, how will that affect this later on? Or what's the best way of doing this? You'll start doing things like, thinking about what's the most efficient way for me to walk across campus to my next class, or, all kinds of things like that. It really, I think it, will help you to think more scientifically and all that kind of thing. So especially since you guys are all scientists, you're all psychologists, I think it'll really help with that kind of thing. It'll help you with your experiment designs and all kinds of stuff. Make you better at statistics, all of that stuff. I like to say it's sort of like, if you guys have seen The Matrix, that moment where Neo sees through the Matrix and he's like, oh, I get it. Like, now I see how everything fits together. You'll start to realize, like, oh, this is how my phone works, and this is why it crashes when it does. Not that you'll actually know how all the code works, but it definitely helps you start to see through like the logic of a lot of tasks, a lot of your computing tasks. I think it really makes things start to fit together a lot more. So anyway, so that's my sort of philosophical reason that I think it's good to learn to program. Practically speaking, I just wanted to like drive home the number of things you can do. So these are all real things that I or friends of mine have coded up in the last few years, like during my PhD and so forth. So you can do tasks with precise timing of rapid stimuli. So if you want to have like images changing 30 times a second or something like that, you can do that, which is hard to do with ePrime. You can generate stimuli on the fly. So if you want to like draw your own stimuli that aren't the same, you're not just showing a picture, but you want to like draw a person with a triangle over their head or something like that for some reason. Or if you want to, like I did a study where we were making masks for fast presentation of stimuli, and the masks were made up of little pictures of the actual face and scene stimuli. We can do that very easily by programming that task, where otherwise we would have had to be in Photoshop for like weeks, like cutting out little pictures of other stimuli and pasting them together again. You can do adaptive paradigms, which you can kind of do in things like ePrime, but it's going to be much easier if you learn to program. So that's where if you want to like do a task where you want everyone to perform at 75% accuracy, and you make it harder or easier as people do better or worse. You can do that kind of thing. You can make complex stimuli. So you might not have ever seen like a dot coherence task, but in like visual psychology, like visual cognitive psychology or cognitive neuroscience, you'll do these tasks where like maybe there will be 500 dots on the screen, and like some of them will be going in a certain direction and some of them will be going in another direction. You can do things like that. You can obviously write tasks that send codes to an eye tracker or EEG or fMRI system, which is a little bit tricky to do if you don't know how to code. You can do things like real-time eye tracking or behavioral feedback. So one thing we would do, like in one of my EEG studies, was show people a little dot on the screen of where their eyes were so that they could see when they were like breaking fixation. So that was really helpful for eye tracking. And at the end of each trial, we'd give them a fixation percentage. So say like, oh, good, you were fixating 95% of the time. Keep up the good work. And of course, you can't do that if you can't write code that like recomputes that number every trial. For data analysis, we've done things like getting really, Wei-Lin has experienced the joy of this, getting like really precise down to the millisecond or below response time data. So like in our work so far, we've done a lot of tasks where people make verbal responses, and we actually digitally record the audio, and then we can look at that recording, which is like sampled 44,000 times a second, and get like down to below a millisecond exactly when someone responded to an item on the screen. If you ever do EEG or fMRI at all, you will have to do some programming at some point. You can do things like outlier removal. So we've written scripts where you like take out your outlying trials and outlying subjects by just running it quickly through a little script. If you do a lot of statistics, you can do what are called Monte Carlo simulations. Do you guys know what those are? Ever heard of that? Okay, so Monte Carlo, is associated with like gambling and casinos and things like that. So it's the idea of like if you have a statistical test and you don't know like the right statistical test to use, you can just sort of simulate it like 100,000 times and see how the statistics break down and see if your results show up more often than you would expect by chance. So you can do things like that. You can do really fancy graphs and charts and things like that, better than you can do with Excel. And you can also do all kinds of other things, like optimize your counterbalancing of your stimuli, all kinds of fun stuff like that. And I will mention that once you learn to do this stuff, if you're a real nerd, you can do things like, these are also things I've programmed in the past, which are not academically related, like organizing your email lists for a party. In my PhD defense, I did this really nerdy thing where I wrote a script to analyze all the emails I sent to and from my PhD supervisor. And I don't have the plot here, but basically we found out that her range of email sending times was like, she would start sending me emails at like 8 in the morning and go till like 7 o'clock at night. And I would start sending her emails at like noon and go until like 4 in the morning. So she thought that was really funny. Well, academic humor. I did a slideshow for my PhD defense where I showed pictures, and like the catchy thing about that was I had a song playing and I had it read in all the pictures in a folder and sync it up exactly so that the slideshow took exactly the same amount of time as the song. Anyone ever play Oregon Trail for the old Apple II? You guys are probably all way too young for this. Okay, yeah, one old person. Anyway, my friend and I started playing old emulated Apple II games, and we hacked the disk image for Oregon Trail so that we could get the high scores. All kinds of things. Oh, and one especially clever thing that a coworker of mine did in my first research job was he wrote a script he called the sleep script. So he had a desk that his computer screen faced the door with his back to the door. So like, he would be like over here. So if you looked in the window, you could see the back of his head in his computer screen. So he wrote a MATLAB script that put up a bunch of like fancy charts on the screen and progress bars and all kinds of things like that. And then he would just put his fingers on the keyboard and go to sleep. And it looked like he was typing and like, making all these graphs and charts all at once, and he would just take a nap. And as long as his head didn't like dip down too much, he looked like he was really hard at work. So all kinds of things you can do if you learn to code, including avoiding work. Okay, so any questions so far about any of that stuff? That's all just motivational speech. Anything? All right. Okay, so enough like cheerleading about programming. Let's talk a little bit about what we're actually going to be doing in this module and what this is. Because again, I think this is like a topic that freaks people out, that's a little bit scary, and people don't really know what programming entails because you see people do it on the movies and things like that. It's not really very realistic. So I think a good way to think about it is that programming is basically a process of translation, right? So the example I would give is that imagine you've got two people at an international airport like KLIA, and one of them is from Germany and one of them is from Korea, and they want to communicate with each other, right? So if you know any German or any Korean, they are not similar languages at all, right? So these people are not going to be able to talk to each other in their native languages. So what you hope, and this is true certainly on this campus and in a lot of places in the world, you hope that maybe both of them speak at least a little bit of an international language like English, which is fairly commonly spoken internationally, particularly in both Germany and Korea, and that they could kind of get by even if neither of those was their native language, right? So that's a little bit similar to what you're doing when you're programming a computer. So basically, your native language is English or Malay or whatever, French. Well, probably none of you are native French speakers, but you have some native language and a native way that you think. And similarly, the computer has a native way that it thinks that is completely foreign to you. But with a programming language, what you're really trying to do is use this intermediate form of communication that can relatively easily be translated to both of your native forms. So if you want to tell the computer, hello, could you just calculate the means and standard deviations of all these numbers and just get that back to me in a minute or two? Your computer would be like 0, 1, 0, 0, 1, 0, etc. And of course, like you're not going to be able, and you're not going to be able to, write exactly in binary to feed directly into the computer's processor. And similarly, the computer is not really going to be able to speak English. So you need something in between that kind of makes sense to you but can relatively easily be translated into computer language. And this is trickier than it seems, right? Because human beings, the way we think, is not at all the way the computer works, right? So we are very like loose and associative, and we don't like to, we don't think in exactly a linear fashion, right? We have these thoughts like, I like bunnies, and, you know, I don't know, psychology is cool, but it's not like everything is like a direct logical process that one thing leads directly to the other, right? Whereas the computer just has to go straight in a line following like a precise logic for everything it does. So what you have to do is you have to take these thoughts that you have, like, I think it'd be cool to have an experiment where like there are like some faces on the screen, and then I don't know, the like, you know, this other thing comes up. And you have to like actually break it down and say, all right, first this comes up for 50 milliseconds, and this other thing happens at 200 pixels to the left of it for, you know, 80 milliseconds, and so forth, right? So it's really the process of taking your somewhat fuzzy, imprecise human thoughts and trying to make them into these very linear, direct computer thoughts. And as a side note, I think this really, one thing is that it's really a lot like, writing a computer program is a lot like writing an essay, which maybe gives you all a bit of a shiver of fear, but you know, that's the same basic problem you have when you try to write an essay, right? Is you have all these, you've probably experienced this when you write your essays, like you have these great thoughts in your head, especially if you're doing a timed exam or something like that, and you're like, I know exactly how you know, the visual system works, and now I'm just going to put it out there. And you spew something out on paper, and it's really actually pretty hard to like convey your thoughts perfectly in a linear, logical fashion, right? To like have nice paragraphs where one leads right into the other, and especially under time pressure, right? You get your essays back and you're like, oh, that's not at all how it sounded in my head, right? So like the process of writing things in a linear, logical fashion where thoughts flow right into one another is pretty hard for people to do. So I think the more you practice it in like this class, I think this will actually in some ways help your human writing as well, we would hope. But it's really kind of a similar process as you say, well, I have all these things I want to say or all these things I want to do, and now I have to write it down, you know, step by step in a way that sort of makes sense and has logical chunks and segments and all sort of breaks apart nicely. Okay, so I should note that computers are getting better at understanding human language all the time. So the classic example of this these days is Siri. You guys have all played with Siri, right? So you can do things like say, Siri, what is the weather going to be like in Kuala Lumpur tomorrow?
It'll be wet in Kuala Lumpur tomorrow.
Okay, great, right? So that's a computer sort of speaking human language. As a side note, Siri has never told me the weather is going to be good in Kuala Lumpur. It's always like rainy every day, according to Siri. But of course, as you can see, like over here, this is not perfect, right? Like people are always complaining about Siri and about the Google version of this all the time. It's not right there yet. You can't say, hey Siri, you know, email all of my friends and tell them to come to a party Friday night, right? Like, because Siri still can't figure that kind of thing out. They will get better over time, right? So these things are getting smarter all the time, but of course they're only going to get better if we program them to get better using programming languages that approximate computer languages, right? So, you know, making computers speak human languages is all well and good, but you still have to sort of tell it how to do that in the computer's native tongue. So that gets into the issue of what programming languages actually are. And again, I don't know how much of this is familiar to how many of you guys, but let's just talk a little bit about different programming languages and what they entail. So there, at the very lowest level, are some very low-level computer languages like binary machine code. So these are the ones and the zeros that I referenced earlier that are going like right into the processor of your computer, right? And it's telling it things like, take this little byte in memory and add it to this little byte in memory and put it over in this memory location, and then take this byte and, you know, subtract it from this byte and put that over here. And if it does that a billion times a second, you know, you have a game or whatever, right? And a very close relative to that is something called assembly language, where you're doing the same thing in like slightly closer to human code. So you're literally writing instructions like manipulating individual bytes of memory. And both of these are like nearly impossible to program in for normal people. So what we've done is we've taken we've written like slightly higher level languages that are slightly closer to how humans think that can be easily translated into these codes, right? So these are languages that you may have heard of or may not, like Pascal, the C family. So you may have heard of C or C++, which are taught a lot in computer science classes. C Sharp, which is used to build Windows applications. Objective-C, which is used to build Mac applications and iPhone applications and things like that. And Java, which you often also learn about in introductory programming classes that is used on the web and things like that. Then you've got really high-level languages like Visual Basic, which is what you use if you want to program within ePrime. It's basically Visual Basic. It's also what you use if you make an Excel macro, like that's written in Visual Basic. Or AppleScript, which is kind of the equivalent on the Mac. There are things, we won't get into any of this really. This is just to sort of give you an overview of how many different programming languages there are in the world. So there's shell scripting, which you use if you're a Linux nerd to automate tasks like moving files and stuff. What you can debatably call programming languages for the internet, like HTML, JavaScript, PHP, CSS, although some of these are really just like formatted text, like HTML is not really a programming language. And there's lots more, like Perl, Basic, Lisp, Fortran, COBOL, LaTeX, and about 100 others that you can see. There's a whole, if you're really interested in this, there's a whole Wikipedia list of programming languages that's several hundred items long. And of course, Python and MATLAB. So the point to make here is not that you need to know all of these things to learn to program a computer, but to know sort of why we have all these things. So, just like humans have a bunch of different languages, you have a bunch of different languages for different tasks. And some of them are close variations of each other, right? So like if you take Spanish and Portuguese, those are very similar, just like C and C++. Very similar languages, a few tweaks, but if you know one, you can kind of figure out what's working in another one. Some of them are really for specific OSs, so like C# is specifically for Windows, Objective-C is specifically for Macs or iPhones and things like that. Some of them, like the web languages, are mostly designed for specific applications. So for example, MATLAB is specifically designed, obviously, for scientific computing. And then, there are a lot of cases where it's even debatable whether certain things are really separate languages from each other, or just kind of like dialects of each other. So, you could think of it like BM versus BI. So, right, like if you speak Malay, hopefully you can kind of speak Indonesian as well. Like there are some differences, but they have basically the same structure, that kind of thing. So the point to make is that there are a million different types of languages with different types of relationships to each other. But just like human languages, they all kind of share some common structural elements. So no matter what human language you speak natively, they all have certain features like nouns and verbs and prepositions and things like that, right? So it's not like there's any language in the world that doesn't have nouns in it, right? And similarly, most of these programming languages, most of them have really similar constructs. So the point to be made is, if you're learning Python and MATLAB in this class, it's not like you're only learning Python and MATLAB. It's going to be a lot easier if you ever want to learn one of these other languages, once you already know one or two, right? So you'll see when we get into the MATLAB part of this course, once you know the Python, the MATLAB's going to be very easy, hopefully. And if you wanted to go on and learn Perl or C++ or something like that, it would be relatively easy if you really wanted to. Okay. Now that brings me into a little talk about, and I know this is not like super interesting, but you'll see why this is all relevant soon. Compiled versus interpreted languages, okay? So this is a really important point to know with regard to both Python and MATLAB. So there's two basic classes of computer languages. Well, there's different types of classes, but for our purposes, there's two major ones we want to think about now. Compiled and interpreted. And the difference is that a compiled language is one that's translated by the computer directly into machine code, okay? So an example is you write a C# program, and that might get compiled into like your Microsoft Office apps. Or you write an Objective-C bit of code, and you turn that into Angry Birds, right? So this is something that eventually becomes an application that you just run directly on whatever your computer is, okay? So what happens is you take the code and it's turned into what's called a binary executable, which is basically the thing that you double click on your desktop or that icon that you tap on your phone or whatever, okay? So the difference is that once this compiling process is done, you don't see the code anymore, like the words that the human typed into their text editor. You don't see that anymore. You just have this icon that you click on your desktop, okay? So you don't need the code anymore when you have a compiled language. Now, an interpreted language is a little bit different. So what happens is, with an interpreted language, you have this text that you write, which is so far similar to the compiled language, but this time you need to run the code through another program called an interpreter every time you want that code to run, okay? So what the interpreter does is it reads through the code line by line, tries to figure out what it does, it generates a little bit of instructions for the machine, and then it executes it. And so basically the difference is, in order to run an interpreted code program, you need both the source code and the interpreter there each time the code runs. And I should mention that these are not necessarily mutually exclusive. You could write a compiler or write an interpreter for a language that's usually compiled or interpreted. But generally speaking, you generally have different languages for each of these tasks. Okay, so that might not make any sense the way I explained it, but here's a sort of real-world example of what we're talking about. So if you have an interpreted language, it might be something like a sheet of music, okay? So with a sheet of music, every time you want to hear the music, you have to give the sheet of music to someone who knows how to play an instrument and say, here, play this. And they look at the sheet of music, and they hit the keyboard, or this is how you play the piano, right, just by flapping your hands. You know, they hit the keys, and they produce the music, right? By the way, bonus credit if anyone can recognize what piece of music this is. I'll tell you next week maybe if you don't know. Versus compiled music, and compiled music would be like a CD, right? So you burn a bunch of songs to CD, and every time you want to hear the music, you just hit play, right? So you don't need someone to replay the music for you line by line every time you want to hear it. You just start it up and it goes, right? So it's just immediately available. Does that kind of make sense? So the difference being, you know, it's very easy to sort of distribute this information, but it has to be reinterpreted every time you encounter it, versus this where it's very easy to like distribute the final form of the information, but one thing you can't do is change it very easily, right? Because if you give someone a sheet of music to play, you can just be like, you know, let's turn that A into a C or whatever. And you can just kind of mark it out and scribble over it, and they know to change it, right? With a CD, you can't like go in and change one of the individual like bits burned onto the CD. You have to just sort of take the final package as it is, right? Oh, by the way, if you're not familiar with the CD, if some of you are kind of young, this is a new thing that all the hip kids are transmitting music on. It's called a vinyl LP, so that might be a little bit more familiar to you if you're super hip. Okay, anyway, moving on. So here's another example, which I will try to launch. So can I have a volunteer who speaks Bahasa Malaysia? It's not very hard. Come on. Anyone? So come on. What's that? Okay, Aiswan just volunteered. So Aiswan, I have. This is going to go to the podcast. I have a copy here of Harry Potter and the Prisoner of Azkaban in Vietnam. Aiswan, what does budak mean? What does lalaki mean? What does gang mean? What does sangat mean? What does war mean? Okay, so you guess the next word is going to be yasa. Okay. I know that. Okay. Oh, this is helpful. What does dalam mean? Okay, what does banyak mean? Okay, all right, good work. All right, so we don't have to go on with that forever. All right, so that was interpreting, right? So like if you hire an interpreter in your job, you know, you have someone that literally like translates something word for word for you. Versus if I had the English version, which someone had compiled for me, I could just read it directly. Harry Potter was a highly unusual boy in many ways. So that's what we were trying to say, right? Okay, good. Thank you, Aiswan. Okay, so the point being there are advantages and disadvantages to compiling things versus interpreting them, right? So an advantage of a compiled thing, as you saw just then, is that if I just had the English language edition right with me, I wouldn't have to say, hey, IceWan, what does this word mean? Hey, IceWan, what does this word mean, right? I can just read it in my native language immediately. So you don't have to retranslate it every single time. And if I wanted to read the book again when I'm done with it, I wouldn't have to then bug IceWan a second time. I would just flip back to the beginning of the book and read it again, right? It's easier to run. So when we're talking about a computer, every time you want to open up Microsoft Word, you just have to click the icon. You don't have to run it through some compiler that translates the written code of Microsoft Word into something you can run, right? So this makes it really good for commercial applications, right? So if you're distributing something that you want, 200 million people to be able to use in exactly the same way, like Microsoft Word or Angry Birds or whatever, it's great for that, right? Because you just give somebody the final version of something. You just translate Harry Potter into, well, it started out in English actually. So you translate it into another language once, and then you print off a bunch of copies and you're good to go, right? You don't have to have somebody translate it or somebody compile the code every single time. Now you might say, if that's the case, why would you ever want to use an interpreted program? But there are a lot of advantages of those too. So the main one is that you can always see and modify the source code, right? So, if you want to see what the program actually does, there's no way to like open up Microsoft Word and see how somebody wrote the code for Microsoft Word to, make a word go onto a new line or, to start a new paragraph or something like that. So that's great if you want to share code and you want to learn things about how something works and take it apart and see how it all fits together. It's really bad for a commercial application, right? Because then someone can just copy your application. And although it's slower overall, so one thing you notice is that if I have to stop IceWan and ask her what every single word means, that's a lot slower than just reading in my native language directly, right? However, it's a lot faster to start running a program if you're running an interpreted program. So, in other words, if I only had a copy of Harry Potter in BM and I wanted to read the whole book, I would have to give it to someone who spoke both languages and ask them to translate the book for me before I could have it, the whole version in English to read, right? So that could take, months. Or in computing time, if you have a big project to compile, that can take a few hours. Whereas if you have an interpreted program, it's running it line by line. So it's ready to run the first line of that program immediately. So it's slower overall, but it's quick to run like one line at a time, if that makes sense. And you can do some neat things like stop it after each line. So you can say, run this line of code, see if that works, run the next line of code, and so on. So that's the line-by-line debugging. So this is all stuff we're going to try out in the Python and MATLAB sections later on. Okay, so the basic moral of the story is that if you have a compiled program, that's best for large projects with thousands or millions of lines of code, like your operating system or your word processor or whatever. If they're self-contained and you want them to work the same way for everyone. And interpreted programs are best for rapid development, testing of small applications with a small user base who might want to fiddle with the code a lot. So, that in mind, which of these do you think applies to Python and MATLAB that we're going to learn today, or in this class? Are they compiled or interpreted? Come on, say it. Okay, yes, I heard it somewhere. All right, so yes, they are both interpreted, right? So the point of these is, these are both things that you don't have to like build some big application every time you write some code. You can just write a line of code and run it directly. And that's going to be very nice because you're going to be able to watch your programs sort of unfold in real time. Okay, so basically we're going to start off writing some very small programs that need to be interpreted by Python and MATLAB in order to run them. And sometimes we just call these scripts. That's a little bit of a terminology. So when we say like, oh, I'm writing a MATLAB script, that's usually some like little short piece of code as compared to like an entire giant project like MS Word or something like that. So this is ideal for learning to program for scientific computing because what you'll find if you start learning to do this stuff is that you're rarely like, you never do the same experiment. Well, you rarely do the same experiment twice, right? You're usually changing at least something every single time. So it's not like, although we would love to have these kinds of numbers, it's not like I'm going to send out like a CD or DVD with my task on it to 1 million people and have them all run my task and send their data back, right? I'm going to run one experiment on 15 or 20 individuals and get the data and say, all right, that's cool. And then I'm going to maybe tweak it a little bit and run another experiment, right? So these interpreted languages are really good for like writing a short little program, you know, that you can tweak a lot and keep running and share your code with others and things like that. And one other nice thing about interpreted languages is they tend to handle a lot of the hard, low-level programming tasks for you. So the nice thing is that you're not going to have to worry about things that you have to worry about if you're writing an application, like how do I open a window? How do I manage memory or things like that? Your language is going to be targeted towards your task. So you'll see that in CyclePy, with just a few lines, you can play a sound or put an image on the screen or something like that that would take a lot of lines of code in a lot of other languages. Okay, you don't have to worry about a lot of those details, but the point is that what we're doing here is going to have a lot of advantages for us for getting up and running really quickly. Okay, so just a few other notes before we jump in and start doing stuff. One issue you might have, or one thing you might be confused about, is speed, right? Because you know, if you're running interpreted code, the question is if your task is going to run too slowly, or you know, you're not going to be able to like put stimuli on the screen fast enough. The good news is that when we talk about interpreted code being slow, that's in very relative terms, right? So if you're running a cognitive task, you can really only change what's happening for the participant every about 17 milliseconds. You guys know what that is? Because you have 1,000 milliseconds in 1 second, and your monitor is probably refreshing 60 times a second, right? You get 60 frames a second on a standard LCD. So that works out to like 17 milliseconds of frames. So no matter how fast you want to change the stimuli your subject is seeing, you can only change them every 17 milliseconds. And that's like forever in computer time. So in that time, even 1 millisecond is plenty of time to run lots of instructions. So the tasks you're going to be doing are going to be way simpler than running something like Skyrim, or running, even Microsoft Word has to do a lot more things per second than your code is going to have to do. So you won't have to really run that many instructions per second. And just to let you know, there are also a few tricks that Python and MATLAB do to run faster. So one little trick is that actually a lot of the tasks you're going to be run actually do use compiled code, and you're going to be using interpreted code to call them. And I don't know if you don't really need to know how that works. The point is that like a lot of the really time-consuming tasks in Python and MATLAB are going to be handled for you, and you're just going to have to like write one little line of code to make it do those things. So it's sort of like saying, if I could ask iSwan to like translate a whole paragraph of Harry Potter at a time, you can get the computer to run a lot of things with just 1 or 2 lines of code in Python and MATLAB. Okay, so like one example is that you know, you can get it to like put an image up on the screen with like 1 or 2 lines of code. Okay. All right. So I know that's probably a little bit high level, a little bit boring. That's just sort of background information that we need to get into before people sort of understand what we're getting into. So any questions about any of that though before we move on to the fun stuff?